In activity 2.11, we're first asked to construct two different equations for the cost of two different cell phone plans. And then in part 4, we're asked to complete a table of values, filling out the cost for each plan compared to different numbers of voice minutes. So in Desmos, we could do this by inserting a table. And if we want to stick with the same contextual variables, we could relabel this as M1. And then in place of Y1, we could input the equation that we would have come up with in part 2, which would be 55.99 plus 0.25 M1. And then in another column, we could input the equation that we would come up with in part 3. And then since we can't see all of that information exactly as presented, that table's getting cut off a little bit. If we move our mouse right over the edge of this kind of sidebar, we can drag that out so we can see that entire table. So now what we can do is plug in values for independent variable m, and our table will automatically fill in by evaluating that first equation and second equation given that variable. Press the down arrow key and we can move down that column for m and fill in our additional values. And our table will automatically be filled out. So you can either have students complete that manually with a scientific or basic calculator, or we can take advantage of Desmos to complete that table of values a little bit more quickly. In part 4b, then we're asked to use the table feature of a graphing calculator to determine the value for m that produces identical c values. So with Desmos, this would come down to simply trial and error. Something that we could do is go ahead and zoom our graph until we start to see these points that we're actually plotting. And through visual inspection, we could notice that they're starting to get very close to each other around 150. So we could have students simply plug in values to try and get closer and closer, but essentially it would be some trial and error. But what they could eventually discover would be that at x equals 140, we're getting the exact same results for both equations. In part 5, we're asked to actually graph the two equations that we found out earlier in the activity. And then in part C, we want to verify our results from part B, which would mean estimating the coordinates of the point where the two lines intersect using technology. So essentially what we want to do, and we could go ahead and hide our previous points just to declutter our solution here. We want to go ahead and graph those two equations that we came up with and find their point of intersection. So I'm going to do this by calling the first equation C1 equal to 55.99 plus 0.25 M1, which actually is giving me a bit of a problem here because what it's actually doing, I realize now, is referencing this column M1 from before. So we could just call this C2 M2. Basically, we just need to give it some index to differentiate it from previous values we've established. So what we have is the equation that we found in part 2, and then we'll input the equation that we found in part 3. So now we have both of our cost equations graphed, and what we want to do is find and verify that point of intersection. To do that, we can simply click on either of the two graphs, either of the two lines. So whether we click on the red line in this case, we see this gray point pop up, or if we click on the blue line, this gray point pops up. We can go ahead and click on that, it'll just highlight it, but what it's doing is giving us that x and y coordinate, which represents the point of intersection between those two lines. We'll be asked to do something similar in question 6, where we'll first solve a system of equations through the substitution method, and then in part E, verify that solution numerically and graphically. So again, we could turn off our existing lines just to declutter our work, and enter our two new equations. Now that we're just using x's and y's, we don't need to worry about indices. It's treating each of these x and y's separately. We can drag or manipulate our viewing window until we get a better view of where those two lines intersect. And then by clicking on this line in purple, we see that point of intersection. In this case, -12, -46. So you will want to be careful here because a couple of other points will pop up. Anytime we click on a line, we'll see the points of intersection highlighted with another line, but we'll also see the x-intercept and any y-intercepts highlighted. So you don't want to direct students simply to look at whichever point is highlighted in gray. They want to make sure they're identifying that point that is in fact the intersection between those two lines. In problem 10, we're asked to graph two parallel lines to demonstrate that there is no point of intersection. So again, turning off the two graphs that we're no longer interested in looking at, we can graph our two new lines. Which initially, based off my viewing window, look like those are almost overlapping or coinciding, but as we zoom in, we can see that those two lines aren't overlapping with each other anywhere. And then through exploration, you could have them drag in each direction to see that as you continue on, those two lines would still never intersect with one another.